I will start introducing you, Domenico, if you're fine with it.
Okay, cool.
Okay, so welcome everybody to this new Ithaca meeting, and let me recall you that next month we will have a physical event, and you can check out the information about the event on the Ithaca webpage. And the first speaker of today is going to be Domenico Fiorenza, and the title of his talk is going to be Categorical Shadows Lurking Behind Integral Formulas for Genera. And Domenico, you can start whenever you want.
Okay, thanks a lot. Thanks to every Ithaca organizer for the invitation. I'm really happy of being here. And so what are we going to talk of today? So we start with this. So I will denote by omega u is the complex cobordist ring. This means that in degree D, we have cobordist classes. Okay, this is just a technical thing, so I'll put it in parentheses stably. D-dimensional closed stably complex manifolds. And the ring structure is just given by, well, sum in the same degree is just disjoint union, and product is induced by the direct product, the Cartesian product of manifolds. And by definition, a genus with values in a commutative ring R is a ring homomorphism from, say, gamma from this ring to R. And we will be interested in genera with values in the field of rational numbers. Genera to Q. So first thing we notice is that this will be equivalent to ring morphism say gamma Q from this tensor with Q to Q, just from the universal property of tensor product. And now the nice thing is that this ring here, once we have read out of torsion by tensoring with Q, has a very simple structure. So this is just a polynomial ring in T1, T2, T3, countably many variables of even degree. So like Ti is 2i, and that is Ti is just the class of Pi. See. So we take the complex projective space of complex dimension I, and this is a generator of the complex cobordist in dimension I. And the fact that we have this very simple algebraic structure for the cobordist ring tells us that gamma Q is equivalent to the datum of a sequence of of rational numbers. Namely, the images of the generators. So AI is the image of TI. Example. This is probably the most classical example. The Todd genus is the genus corresponding to AI equal 1 for every I. And at least for the Todd genus, we have some famous formula that tells me that the if say X is a compact complex manifold, then I can look at X as an element in the coboarding string, so I can consider the image of X through the gene to the Todd genus. So this is what is called the Todd genus of X. This can be expressed by an integral formula. This is the integral over X of some specific cohomology class called the Todd class of X. This is a certain cohomology class. And one may suspect that this is true because of this particular choice of the constants. So the fact that every projective space is assigned genus 1, but actually it is not so. So what is true is the Hirzebruch genus formula that tells us that for any genus gamma, there exists a universal cohomology class Todd gamma. By this I mean that for any manifold X, we have a class Todd gamma of X, which is natural with respect to morphism of this in a more precise way. So for any manifold X and any complex vector bundle V over X, we have a class called F V, which is natural with respect to morphisms of manifolds, Ulbecks of bundles. That is Todd gamma of F star V. Yes, F star Todd gamma V. And then Todd gamma of X is by definition Todd gamma. So there is this universal cohomology class Todd gamma such that the image by a gamma of the class of X is the integral over X of this class. So what I'll try to convince you during this talk is that this kind of formula should not be surprising at all. This is precisely the kind of formula we should expect. And I'll try to derive this formula from general categorical constructions. After all, this is an Ithaca talk. So the first thing we need is the category of spectra. As a setting for cohomology theories. So the idea is that we move from topological spaces, which are, well, when I say topological space, I always mean a nice topological space. So something which is at least homotopy equivalent to a CW complex. So topological spaces are where cohomology theories start with. So a cohomology theory is defined as a functor on topological spaces with some properties, what is called the Eilenberg-Stein reductions. But then this naturally leads to introducing another object, which is called a spectrum. A spectrum is what represents the cohomology theory, and it is better to work from the very beginning within spectra. Now, what are spectra? So defining spectra would take all the time. So I will just talk of them through an analogy. So to a topological space is associated a spectrum. And the motto is spectra are two topological spaces, just two spaces, as real numbers are two rational numbers. What do I mean by this motto? I actually mean two things. One is quite concrete. So spectra can concretely be defined as certain sequences of spaces, just as real numbers can be defined as certain sequences, or better, equivalence classes of sequences of rational numbers. But what is most important in this motto is that when you work, at least when I work with real numbers, I almost never, and I think for what concerns myself, I can confidently say never work with the definition of real numbers as equivalence classes of Cauchy sequences of rational numbers. I just use axioms of real numbers. And I basically just use the fact that every rational number is also a real number, and real numbers have some additional properties. They are a complete field. Actually, just a side note, if you say ordered complete fields, you are saying real numbers, because you could actually prove that the unique ordered complete field is that of real numbers. So to stress that how much the axiom is what is relevant here. And of course, Cauchy sequences of rational numbers are not something that is useless, but we can think of them as the proof that a field with those properties does indeed exist. So in this talk, just trust me that a category of spectra exists, with the property I'm attributing to it, and the actual construction of spectra as limits of topological spaces, as sequences of topological spaces, is a proof of the existence of such a category. Okay, so the idea is that we have topological spaces. These are not just a category, these are a monoidal category with the product. And we can freely add a base point to a topological space and move from topological spaces to pointed topological spaces. And this category 2 is monoidal with a product which is called the smash product of pointed topological spaces. And adding a point is a monoidal functor. And then from a pointed topological space, I can construct a spectrum, which is just the sequence of all the suspensions of the space. So I will denote this by sigma infinity. And here I have an extension of the smash, which is called the smash product of spectra. But for this talk, to stress that this is my monoidal product, I will denote it by tensor. And both these functors are monoidal. So we have a monoidal map from topological spaces to spectra. So an important difference with the case of Q inside R is that Q embeds into R. Topological spaces do not embed into spectra. This morphism is not fully faithful. So you actually lose some information on a topological space when you look at it as a spectrum. What you retain is the stable information. So let me write this. So if X is a space, sigma infinity of X plus retains the stable information on X. Okay, but although there is a difference between X as a space and X as a spectrum, it will be convenient to use the same symbol. X, both for X as a space and for X as a spectrum. Okay, so first important point, spaces are spatial inside spectra. Indeed, if I have a space, X, this has a terminal morphism to the point, and it has a diagonal morphism from X to external X. So when I look at this through spectrification, I'll have a map from X to the terminal, so the point, which is the terminal object, so is terminal object in top, but it is also the monoidal unit. And a monoidal functor needs to satisfy no compatibility with terminal or initiality of object. but it has a compatibility with monoidal units. So the monoidal unit for spaces will go to the monoidal unit for spectra. Just for the note, this is called the sphere spectrum, since its nth component is just an n sphere, Sn. And then the diagonal gives me a morphism from X to X tensor X. And these two maps here make X a comonoid in top. So every topological space is naturally a comonoid with the co-unit given by the terminal morphisms and the co-multiplication given by the diagonal. This means that spaces are comonoids in spectra. So they're special. Not every spectrum is a comonoid. So the second ingredient we need is, we consider now a monoid E in spectra. So something that comes with a multiplication and a unit. And we will call this a ring spectrum. And if multiplication and unit are form something which is commutative, if it is commutative, let's say up to homotopy, better up to given coherent homotopies, we call it E infinity ring spectrum. Okay, now so let's take X a space, E a ring spectrum. Then we have a comonoid and a monoid. And the two together give us a monoid. What is the composition? Well, it is the obvious one. This is completely general. We take tensor product, go to X tensor X, E tensor E, and then we use multiplication and co-multiplication. So something more can and should be said is that spectra is an infinity stable category. This means we have homotopies between morphisms, homotopies between homotopies and so on. And this is the infinity part. And stable means that there exists a zero object. And there are finite limits and colimits, and every pullback diagram is a push out and vice versa. And notice that this is meaningful just in the infinity setting. For ordinary one category, if you ask this property, you just end up with the trivial category. And this fact allows for the formation of loop spaces, and so suspension and the suspension, given an object X, we can form this pullback and call it omega X, or X shifted by -1. While to form the shift by 1, we start with X and form the push out. The fact that every pullback is a push out, you see that if you start with X -1 and you shift it by -1, you correctly get X. Okay, so what is a convenient fact of this? Is the fact that since we have that forming essentially the universal property of pullbacks tells me that if we take two spectra, X and Y, we consider the space of morphism from X to omega Y. This is the loop space on the space of morphism from X to Y. And now I can write that Y is Y Q minus 2. And so morphism from X to Y are morphism from X to YQ minus 2. This is morphism from X omega 2 YQ. Now omega 2 goes outside, and this is okay. Now notice that above I had written square brackets to mean morphisms. Indeed, this is the home set of morphisms, and it is the set of connected components of the space of morphisms. So if I take connected components here, I see that the set of morphisms from X to Y is pi2 of the space of morphisms from X to another spectrum, Y2. But now this is pi2 of something, so this is an abelian group. This is true for any xy, but in the particular case, y is E. Then we have both an abelian group structure and a multiplication on E. And any that X is a space. Okay, one can check that the two are compatible. And make this is a ring. This is the cohomology ring of X with coefficients in E. Actually, from the point of view of cohomology theory, this is just the 0th cohomology ring, the 0th degree. If you want all the degrees, this is the 0 degree component of graded cohomology ring, which is just taking the direct sum of X En. But actually, what really matters is the 0 component. In the setting of spectra, looking at the other components is just home spaces between shifted things. So structurally, there is no difference. Okay, so far for the home space, but now the second main ingredient is vector spaces. And their Thom spectra. So we take V, vector bundles, of course. So we take V, a vector bundle, a real vector bundle over space X, and then we can form the following space, which is called the Thom space. So this goes inside V. Of course, this as a terminal morphism, and the homotopy push out here, it's called the Thom space of V. And okay, this is naturally a point space. The natural pointing is just the lower horizontal map. It's part of its definition. It comes from with a map from the point. So it's sigma infinity is a spectrum. This is the Thom spectrum. That currently, with what I said before in this talk, we will just denote by the same symbol. No, maybe here better use another symbol, which is more convenient. And I will denote this. By X to the V. Okay, so if I start with X as space, then I have X as spectrum. But if I start with a vector bundle, then I'm forming a pair X, X1. So this is not just a spectrum. This is a monoid in spectrum. And now here I have a pair. And another object. And the nice thing on this object from a categorical point of view is that this is a comodule over X. So what are vector bundles in a classical topological perspective become pairs of a comonoid and of a comodule over this comonoid. But then this means that if we take E and a ring spectrum, then XV E is a module over the ring X E. And not only this one, also of course, all is shift. Okay, so now it comes the almost final principal ingredient here is that not only spaces are special inside spectra, but closed, I mean compact, without boundary. Smooth manifolds are special within spaces seen as spectra. And to say what I mean by this, I have to talk of the last categorical property of spectra that we are going to use. And it is that spectra is monoidally closed. So spectra of Y tensor X, Z can be written on spectramorphism from Y to some sort of space of maps from X to Z. And one gives a definition, the Alexander Spanier dual of X is, well, it is what you imagine is the object Fx S. So this means that spectramorphism from Y tensor X to the sphere spectrum are the same thing. spectrum of from Y to the dual. To the dual of X. Okay, so as every factor, so as every construction defined as homes to, well, defined from an universal property as the one defined F, we have that X going to the X is a contravariant factor. And also that S is self-dual. Okay, so contravariancy plus self-duality of S tells me that since X was coming with a co-unit, then we have a distinguished morphism from S to the dual of X. This for any space. And now I can tell you what makes smooth manifolds special. The dual of X is the Thom space, the Thom spectrum, X to the minus tangent X. So I should have said before that all this extends from vector bundles to virtual vector bundles. So things that are formal differences of actual vector bundles. Okay, so let's go to the conclusion. So we use this fact to define an integration. So we need one last definition, which is an E orientation of X. So we say first that we say that X is E orientable if, okay, we say that this is, so remember, this is a XE module, this for any n. We are interested in a specific n, which is just the dimension of X. So we say that X is E-orientable if this is a rank 1. XE module. And an orientation, an E orientation, is a module isomorphism. And now the next thing, since this has rank 1, 2 orientation will differ by multiplication by an invertible element in X. Okay, back to integral formulas. We use orientations, so E orientations leads to E integration. What do? We start with X E, and then we use, let me give a name to this isomorphism, and let me write it in the other direction. Let me call this sigma. I can use sigma to go from this to X minus Tx dimension of X E. But now I remember that X minus Tx is the dual of X. And remember that the dual receives a map from S. So since here I have a map from S arriving here, I will have a pullback map. So let me give a name to this map. This was phi X. So here we have the pullback phi star that goes S. Dim X. Okay, so what is this? So this is just
Domenico, pardon if I interrupt you. You're already over time.
Oh, right. Sorry, it was not a. So sorry for this. I'm concluding. So, okay, so this is just one of some abelian group, and this is the general version of integration. And now, where does that factor we were talking at the beginning appears from? So, two orientations differ by a multiplicative factor. So, two integrations will differ by a multiplicative factor. And we consider two cohomology theories. So, two E infinity ring spectra. Just mu, which talks of complex properties, and HQ, which is just the usual cohomology with Q coefficients. And we have a natural morphism from here to here, and this induces this natural morphism. This induces the genus formula. Sorry for having gone over time. At some point, I got convinced. I was constantly looking at the clock, but I was convinced at some point that it would have ended at 30. Sorry.
It's okay, no problem. So thank you very much. So would you say you are finished?
Oh yes, this can be a conclusion.
Okay. So thank you very much, Domenico, for the nice talk. And now we open to question time. First, we have our round of silent applause, which is silent, so you cannot hear it. And so now we open question time. So if someone has questions, just unmute your mic and ask.
Ask a quick question about a construction in the beginning.
Yeah, sure.
So you started with topological spaces, and then you adjoined a base point freely.
Yes.
Which I'm assuming just means take the disjoint union with the point.
Yes, that's
right?
it. Just disjoint union with a point.
Perfect. So for spaces that already start with a natural base point, like the cone on some other space, and then when you take the suspension to get to spectra, don't you? I would assume that adjoining another base point loses like a lot of structure on the space that you start with, because it already has a base point, right? So if you join another one,
yes, you completely forget about the previous one, and the new base point is the new one. So indeed, as I said, the map from spaces to spectra is not at all faithful.
Oh, okay.
You are losing a lot of information.
Okay.
You are retaining a lot. So you're retaining what is called the stable information. So that information that survives after all suspensions. Well, if you start with pointed spaces, so you retain the information that survives to all suspensions. And if you start with spaces, you retain the information that survives to this funny operation of first adding a point and then suspending.
So is there a pedagogical reason as to why we're starting with topological spaces instead of directly with pointed spaces?
Oh, it's mostly historical, I would say.
Okay, thank you.
I mean, spectra are much more close to pointed spaces than not to spaces in the beginning. But then cohomology theories are for spaces, just spaces.
Okay. Yeah.
And the way between the two is just adding freely a point.
All right, thank you.
Now you're welcome.
The rule hasn't changed, so if someone has a question, just unmute your mic.
Maybe a very elementary and boring questions. You said that you can recognize spaces inside spectra as being cohomoloids.
No,
I don't
you don't really recognize them. They are special in that they are cohomoloids, but it is not true that, at least I don't think it is true that a cohomoloid in spectra is a space.
I don't think it either. So
no, I don't think it is true.
Yeah, but
I do not have an example just on the tip of my mind, but I don't think it is true.
So, but are you aware of a theorem that characterizes spaces as in spectra as cohomoloids, such that blah 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 series of assumptions?
Never heard of that. There could be a characterization, but I'm not aware of that. So for sure they are cohomoloids, and the importance of them as comonoids is that essentially from the very beginning on, all the construction you do in cohomology theories use this fact. So they hold for comonoids in spectra rather than for topological spaces.
I would expect that some, like an H comonoid has information in higher levels about co-associativity and co-unitality up to homotopy. A space probably doesn't, or it's like one truncated in this.
I don't know, because well, classical theorems are those that recognize some loop space within such a spectra by looking at the possible En operant action on it. But just a bare space, I don't know if there's some, if there's the degree 0 part of the Merey-Koenigsegg theorem, I don't know. Something that tells this is a space just by looking at its categorical properties within spectra.
Okay.
That could be, I'm not aware of.
We can think about it together.
Okay, so I think we could have time for one very short question. But if we don't have it, then we thank the speaker one last time. Thank you very much, Domenico, for joining us
Thanks a lot
today.
again. Sorry for the delay.